Okay, so let us start. Last what we did is we see something called B stability, and we see the definition of B stability, and then we see a alternate condition or an alternate way to verify B stability, right? Except by using the definition, right? So we have an alternative definition or alternative mechanism to verify the B stability, right? So that we write that as a theorem, but skip the proof at that time. So first I will do an example of that theorem, and then we will see if we can do the proof in time or not. Right. So here's the example. Okay, so suppose the Ranguta method is given like this, right? So now you know all these things. This is going to be an implicit Ranguta method, right? C naught, C1, B naught, B1, or B1, B2, C1, C2, and so on, so on, so on. And so then you know, right? So you can define the following, right? So you know that the capital B matrix is a matrix, a square matrix with Bi being the diagonals. So in that case, you clearly know that your B is 1/2, 0, 0, 1/2. And also you can easily see the A, right? So that is a matrix of 1/4, 1/4 minus square root of 3/6, 1/4 plus square root of 3/6, and 1/4. Okay, so that is your A. So you can find A inverse, right? Because you know, if you look at the theorem, you are supposed to use A inverse, right? In the theorem, right? So when you see the Q, you have like B, A inverse, blah, 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 and things like that. So you need to find A inverse, which is second year linear algebra work. So let me write down A inverse directly. So you all know that, right? So this is 1 upon a determinant of A, right? A into adjoint of A, right? So this is the formula for A inverse, which you all know, right? So you can figure this out. So let me write the answer directly. So it's going to be 3, -3 minus 2 square root of 3. This is -3 plus 2 square root of 3, and this is 3. So this is your A inverse. Right, so you know that first thing, you know B is clearly positive definite, right? So B is this, right? So for any vector X, right? So you can, there are two ways to verify that. Right? One is this. So let me show you both the ways, because this is a simple example, right? So one is either right. So one way to show that it is positive definite is because the eigenvalues, it is a diagonal matrix. So the eigenvalues are diagonal terms. So you all know that it's half and half. So they are positive. All the eigenvalues are positive. So it is a positive definite matrix, right? Because B is clearly positive definite because, or you can go the standard way of showing the positive definiteness also, right? Right. So if you multiply this, right? So basically this is what you have to do, right? X transpose Bx is something you have to find, right? So for X is a column vector, so you know this, right? So this turned out to be, if I do the math correctly, this has to be x1 squared plus x2 squared, right? Right. So this is x transpose bx for all x non-zero. So for clearly for x1 and x2 non-zero, you compute row into column x1, half x1, half x2, and then you multiply then half x1 squared, half x2 squared. So it's going to be half of x1 squared plus x2 squared. And because x1 and x2 are non-zero, you know this is strictly positive. So both ways you can show that it is positive definite, right? But the theorem says it has to be positive semi-definite. So here positive definite is automatically positive semi-definite, so you don't need to worry about that, right? So that part is okay. B is clearly positive definite, so it's obviously it comes under the case positive semi-definite case. So now the problem is you have to look for Q, right? The other one, Q. Give me a minute. Huh? Okay, so that's the first part. Now the second part is you want to get Q, right? You want to get Q, and you have to have Q to be positive semi-definite as well. So for that Q, you need to have the following formula. As first and next, you need to find this matrix Q. The Q is this, right? BA inverse plus BA inverse quantity transpose plus B transpose A inverse transpose B transpose A inverse. Okay, so you want to compute this, right? BA inverse. So once you find BA inverse, you can find BA inverse transpose, right? And again, once you find B transpose A inverse, then you can always find B transpose A inverse transpose, right? So this is just matrix multiplication. So you can do that. So according to this node, it's says when you get this, you get 0, 0, 0, 0. So Q turned out to be a zero matrix. So in this matrix is clearly positive, semi-definite or non-negative definite. Okay? Positive, semi-definite. So in that case, you know that B is positive, semi-definite, or definite, so it's automatically positive, semi-definite. Q is positive, semi-definite, so it is N. Hence the method is B. Okay, so this is an example of how you can use this matrix Q and B to define B stability, right? So this is according to the theorem, right? If the matrix B and Q are non-negative definite or positive semi-definite, then the method is B stable. So last time I told you the proof is lengthy, and so it is lengthy, but what I'm going to do is I'm going to try to show you the proof as much as I can, right? So we will see whether we will be able to finish it today or not, right? So it is a lengthy proof, but that is what I'm going to do now. I'm going to start proving the results. So here, what I'm going to do is I'm going to assume that the matrix B and Q are positive semi-definite, right? So proof of the theorem. Right, so if the matrix is Q and B are non-negative definite, then the RK method is B stable, right? So we want to show that. Okay. Okay, so proof. First thing, so first claim is this, right? So if Q is non-negative definite, right? So positive semi-definite actually. Uh, so then Q cross IM is non-negative definite, right? So we have to. This is the first claim in the proof. So for that, you know that this is a big size matrix, right? So IM means identity matrix of size M cross M. Huh? That's the notation. Right? So now what we need to do is to take, right? So let us take a vector X, right? So which is again the collection of vectors or vectors arranged one on top of the other, right? So each vector is in Rm. So altogether the vector S is of size Sm, right? Because each vector is of size M and you are placing S such vectors on top of each other. So it's a size of Sm, right? So you know that it is one, sorry, Sm plus 1. Right, so this is of size Sm plus 1. Okay, so now you have a non-zero vector. So as beta I is non-zero for at least one I, right? So you clearly know that X is non-zero, right? So you know X is 0. So now because this is non-definite, non-negative definite or positive semi-definite, this is tensor product. Huh? Okay, so what we do is we write Q as a element-wise matrix multiplication notation, right? So that means the ijth element of Q, right? So basically, right? So the ijth element of Q, we write this as a matrix notation, so element-wise notation of this matrix multiplication, right? So you know that B is B1, B2 up to the diagonal matrix, and then the diagonal terms are Bi, and then you multiply that, so that, right? So you can write down the general term, and then you can figure out the ijth component of each matrix multiplication, and then you can write it down. Right? So this is the matrix by multiplication. One check about that. Right? So maybe there may be some mistakes in the notation, but you can always double check. No good. So now what we are going to do is to use, remember that the original definition of B stability is something like this, right? So you know that, right? If you recall the definition of B stability, at the very beginning of the B stability, this is how to define, right? Norm of yn plus 1 minus yn plus 1 bar. So they are two different numerical solutions obtained for two different initial values. Therefore equal to yn minus yn bar. Right? So if that is true for all n, then we say that it is B stable. The method is B stable. So in that case, we basically want to compute this norm and this norm, right? And then we have to compare both of them. That is what we have to do. So we will now start building up work which will help us to compute these two terms. Let us define these notations, right? So you know you want to get yn and yn bar, then yn plus 1 and yn plus bar, and then the difference in the original solution and stuff like that. So you can right? So, but we know that you can write the Ranguta method in a matrix form, right, as a single matrix equation on this form, right? So these are y n plus 1 for, and you put all the vectors there together, right? And then this is for another initial value, right? So we see that we can write them in a general form like this, right? So in this sense, we can see that when you subtract, okay, so when you subtract one from the other, you get this. So now what we are going to do is we are going to write these element wise. We have a lot of notations which makes it a little more confusing, but these are we already defined, right? So when generally we have the Ranguta method, you can generalize that with this form, right? Then you can write down the formula for the basic. This is what we are doing here. So from this, what you can do is you can solve this for this. So 8 times so you solve this for h times f of y minus f of y bar, right? So then you know that it's going to be this a. Right? So you move x and x bar to the other side and combine y and x together, and y bar and x bar together. So you get y minus x minus y bar minus x. Then you move the matrix A cross I to the other side, so you get A cross I inverse. So now this is the individual term of this, right? So that is you remember that in x every term is yn because in the formula you know it is yn plus so on, yn plus so on, yn plus so on. So every component in x is a vector yn, right? But the component in capital Y are yi, right? So then you know that it is this. And so if it is X bar, you know it will be. That's basically. That's going to be. Yeah, so again, you rewrite this. So yi minus yi bar vi, then yn bar minus of yn minus yn bar. So now, okay, but if you look at the Ranguta method for two different initial values, remember this whole thing is about applying the method to an autonomous system. So f is f of y, right? So not f of t comma y. It's always going to be f of y. Right? So that this is the original Ranguta method, right? Yn plus 1 is equal to yn plus 8 times j dj by j. So if it is bar to another initial value, you will get this form. Right? So from this, again by subtracting, you can see that b is going to be b naught plus j is equal to 1 yes dj into j. Right? So when you subtract one from the other, you get this. So now comes the big part, right? So we consider right 2 norm of v squared. That is basically inner product of v dot v. Right? So you take the inner product of these two. Okay, so you take the inner product of these two, right? Okay, so this turned out to be this. you simplify this inner product, you get this, right? So this is V naught and so on. Okay, so then what happened is you will get, again, it is about simplifying the inner product, right? So that's a lot of mechanical work, right? So eventually you will get this. So let me write it down. So the first one is, V naught 2 norm squared. Second one, you take the summation out. Okay, so here we are doing just a little manipulation, right? So 2 times V naught comma Bj Wj, you write that as 2 times Bj Vi comma Wi, sorry, Vj comma Wj. And then you do this. So eventually, by combining these two, you will still get this term. Right, so that's the idea here. Right, so you do this manipulation. So now what you do is you have to make the necessary substitution for Wi and or Wj, right? So you have a formula for Wj, right? So earlier, and you have to do all the substitution, right? So after making all the substitution, this is what you are going to get, right? So I'm skipping the substitution part and simplifying part, and I'm going to write it down directly, right? Just to save time. So it's going to be V naught quantity squared plus 2 times J is equal to 1 to S Vj into Vj comma Wj minus summation of I comma j running from 1 to S Qij into Vi minus V naught comma Vj minus. Okay, so when you do the substitution and simplify, you get this, right? So this form, right? So now, so basically you have this, right? So eventually, if you look at this last line, okay, so if you look at this last line, you have 2 norm of V squared is equal to 2 norm of V naught squared plus a term, right, minus a term, right? So, but this minus term, right, so this term is positive because you already know using the fact that Q is positive definite, right? This term is a plus term, right? So you know that what you have in the last parenthesis, this term is plus, right? So minus of plus there. So now what you have to do is you have to show that this one is negative, right? So if this is negative, right? So eventually V2 norm squared is V naught squared minus something, right? So V2 squared is V naught squared minus something, minus this one also minus, so minus something. So this implies right. So if that is true, then you know V squared is V less or equal to V naught squared, and both are positive, so you can take the square root. So that gives 2 norm of V is less or equal to 2 norm of V naught. So this is what you have as this. Right? Remember, this is what you have. So now this one is positive. You all already know, right? Which we have proved. So now what is left is you have to show that this thing is negative. Right? So that's all you need to do.